I'm going to do some examples of optimization problems, which come up in section 4.7. So usually the first thing I do with optimization problems, after reading the problem, is I try to think of what is the quantity that we're trying to optimize here. So optimize just means minimize or maximize. So here I have find two numbers whose difference is 100 and whose product is minimum. So the first thing I notice is that the product is the thing that we're trying to minimize here or optimize. This means that I'm going to need to find a function for the product. I need a product function because that's the only way I can use the techniques of sections 4.1 and 4.3 to optimize this quantity. I have to express it as a function. Then I think about, well, what am I being asked for? I'm being asked to find two numbers. Okay, so this is what I'm really being asked for, the two numbers that have a difference of 100 and a product of that's minimum. Okay, so I start with my unknowns and I start declaring my variables here. So let x and y be the two numbers. Okay, the next thing I'm going to do is I'm going to try to create this function that I need. So I'm given that the two numbers whose difference is 100, so that immediately lets me know x minus y is equal to 100, and whose product is minimum. So I'm talking about the product is p is equal to x times y, and this has to be minimum. Okay, so these are the two equations I get from the problem. Now, this equation implies that y is equal to x minus 100. And I can take this expression for y and substitute it into the product in order to express the product completely in terms of x. So if I plug this in for y here, then I get that the product is equal to x times y, which is x minus 100. The key now is that I now have the product expressed as a function completely of x. So I can write it as p of x is equal to x squared minus 100x. Okay, and this is my product function. The domain of this function, well, there are no constraints put on the two numbers, so they can really be any real number. Okay, and so this is my product function. So the nice thing is once I have it expressed as a function of one variable, we know from section 4.1 and 4.3 that I can find the local maxes and local minimums of this function. So in this case, my interval is open. So I need to use the techniques of section 4.3, which means I need to use derivatives to detect where the function is increasing, decreasing, increasing, in order to detect the local maxes and mins. So let's do that. So in order to optimize this function, I take the derivative and I get 2x minus 100. And I want to find the critical numbers. This function is always defined, so the only critical number that I'm going to have is where this derivative is equal to 0. So 2x minus 100 is equal to 0 if x is equal to 50. Okay? This is the only critical number that we have. Okay, so if there's a local max or min, it had to have occurred here. So I'm going to test it. Okay, so we found the critical number, and it's the only critical number, and we need to test it around. Okay, so I'm going to look at the derivative, the sign of the derivative. If I choose the value 1, then I find that the derivative is negative. So the derivative is negative over here. Let's choose the value 100. And in this case, we have 100 minus 100, 200 minus 100, so the derivative is actually positive. What this tells me is that the product function is decreasing here and increasing here, which you could tell anyway because, the product function is just a quadratic function. It's just a parabola. Okay, so the minimum is achieved. There's a local minimum at 50, but because this is the only critical number, this is actually the global minimum. And we've proved that the minimum is achieved when x is 50. So to finally answer the question, the original question asked us what the two numbers were. The two numbers are x equal 50. And the second number, well, we know y is equal to x minus 100. So 50 minus 100, so negative 50. So in other words, what this is saying is if you take any two numbers whose difference is 100, the minimum product you're going to get is when one number is 50 and one is negative 50, so negative 2,500. Okay, so I'm going to do another example. Here we're trying to find the dimensions of a rectangle with area 1,000 meters squared, whose perimeter is as small as possible. Now, most of you probably know, or some of you probably know, that the perimeter is going to be minimized when we have a square. So in a way, what we're really doing here is we're proving that. And I'm just really using these examples to illustrate how to solve optimization problems. So I look at the problem and I said, well, what am I optimizing here? Well, I'm minimizing the perimeter. Perimeter as small as possible. So the minute I see that, that I'm optimizing or minimizing the perimeter, I know that I need a perimeter function in one variable. I also take a look at what it is that I'm searching for here, and the unknowns are the dimensions of the rectangle. Okay, so the length and the width. So again, I start off by letting my unknowns have a name. And I'm just going to draw a picture here because it's pretty obvious. X is the width, Y is the length. Next, I move on. So after I give my unknowns a name, I try to construct this perimeter function. So when I read the question, it says, find the dimensions of a rectangle with area 1,000. So I'm immediately given that x times y is 1,000. And I know that the perimeter is what I want. So P for perimeter is given by 2x plus 2y. Okay, so these are the two equations I have. Now, I want the perimeter in terms of one variable because those are the only types of functions I know how to maximize or minimize. So I look at this and I see y is equal to 1,000 over x, and then I plug this y into this expression for the perimeter, and I get the perimeter is equal to 2x plus 2 times 1,000 over x, which is nice because now I have a perimeter function in terms of x. It's p of x is equal to 2x plus 2,000 over x. My domain here, well, x represents the width. So the only sensible domain is that x is a positive number. Again, this is an open interval. That means that I'm probably going to be using the techniques of section 4.3 as opposed to 4.1 with the closed interval method. Okay, so keep that in mind. My next step is to optimize, or in other words, minimize p. So p prime of x is equal to 2 minus 2,000 over x squared. I want to find the critical numbers of this function. So I ask where is it equal to 0. So I have to solve this equation. 2 equal 2,000 over x squared. If only x squared is equal to 1,000. And then we get x is equal to positive or negative, which is the same as x is equal to positive negative 10 root 10. Now I can throw out the negative value because width is never negative. Okay. So this is the only relevant critical number in this domain. The next thing I'm going to do is I'm just going to use the methods of section 4.3 to prove to you that this is indeed a local minimum. And since it's the only critical number, it's going to be a global minimum. So we take, let's see, 10 root 10. Let's see, so I'm going to root 10. 10 is between 9 and 16. So root 10 is somewhere between 3 and 4. So I'm going to choose, let's say, 2 for my test value here, and 10 for my, 2 for my test value. That's clearly going to be less than 10 root 10. And then since root 10, I'm going to choose maybe 100. Because if this is about equal to 4, this is around 40. So I'm going to choose 100 as my other test value. So p prime of 2 is going to be positive or negative. Well, it looks like it's going to be a negative number. P prime of 100, well, 100 squared is 10,000. 2,000 over 10,000 is a number less than 1. So 2 minus a number less than 1 should be positive. Right, so p prime of 100 is positive. So you can see that because of p prime, my function p is decreasing then increasing. Since this is the only critical number, this has to be the global minimum. Okay, and this was, remember, the length, or the width. So to answer the final question, the dimensions that maximize or minimize the perimeter are 10 root 10 by, well, if x is 10 root 10, then y is also 10 root 10. So it's a square. Okay.